All right, we'll keep going with these notes. When wax freezes, or any other substance for that matter, is energy absorbed or released? Well, we've already talked about at these phase changes, specifically with the freezing phase change, the arrow goes to the left, so energy will be released. And you need to know how to answer that question for each one of these phase changes. That melting would be absorbing heat. Vaporization is also absorbing heat. It goes to the right, whereas condensation will lose heat. It'll release heat to go from gas to liquid. Okay, and you need to know that qualitatively, but also we need to know how to figure out exactly how much heat is released and absorbed, and we can do that very easily by looking at the graph. So for instance, how much energy is absorbed by this water during the melting stage? Well, here's the melting stage right here. And you'll notice that when we begin melting, the substance contains 10 joules of energy. And when melting is finished, all the substance is now a liquid, you have approximately 30 joules of energy. Which means that from here to here, you had to add 20 joules of energy to bring that about. Okay, so during the melting stage, you start with 10, and you end up with 30, and that's going to be well, let's just do big minus the small. 30 minus 10 gives us 20 joules, right? In other words, all you need to do to answer these types of questions is to figure out where you're starting and where you're ending up, and what's the difference between there. How much energy was added, or how much was taken away if we go the other direction, right? If it said how much energy is released by water during the freezing stage, it would be the same answer, because freezing is the same process, just the other direction. How much energy is absorbed to bring the water from freezing to boiling? And that means from the end of the freezing stage to the beginning of the boiling stage. Okay, so we started with 30 joules of energy, and at this point, if we draw a line down, we have, let's see, it's kind of crooked, isn't it? You end up with 90 joules. So 90 joules minus 30 joules of energy gives us 60 joules absorbed to bring the water from freezing to boiling. Now remember, this is specific for a specific mass of water. In fact, this probably wouldn't be very true. These are very, very low energies for water. This would be a very, very small mass of water, you could say. During the condensation phase, how much energy is released? All right, so here's condensation. You start condensation at, I'll call that about 125 joules, and you end the condensation at 90 joules. So we'll say 125 minus 90 gives us about 35 joules of energy that's released to bring the water from a gas to a liquid. Okay, so those problems are pretty simple. You just need to be able to look at a graph, and it's very important to know where all of these things fit in so that you can then know where you're starting from, where you're ending up, and the energy difference between those two places. It's pretty simple. All right, let's keep going. Number 9 down at the bottom of the page is also a very interesting question. Sally Noodle is cooking pasta in a pot of boiling water. Will the pasta cook faster if the water is boiling vigorously or gently? And explain that. I want you to think about that on your own, pause the video, and come up with the answer. Okay. Hopefully, the answer that you could come up with is that it really doesn't matter. So will the pasta cook faster if the water is boiling vigorously? No, it will not. And the reason is this. Boiling water is at 100 degrees Celsius, and it doesn't matter if you're boiling vigorously or gently. It doesn't matter. If the water is boiling, that means that we're somewhere up here in this vaporization stage, and you have both liquid and gas present. As long as both the liquid and the gas phase of water is there, and as long as you're in this vaporization stage, notice that there is no temperature increase. In other words, the energy that you are adding to that substance, remember, goes into changing the molecular structure. It does not go into increasing the kinetic energy of the molecules. And it's the kinetic energy of the molecules that's going to cook the pasta. Okay, the kinetic energy of the water molecules will influence the kinetic energy of the pasta molecules and that'll change the temperature of the pasta. It'll cook the pasta. And so the correct answer to this is that it doesn't matter whether you boil vigorously or gently. And go home and try it for yourself. Go home and try it for yourself and prove to yourself that it doesn't really cook any faster. Now, I know all of us have seen recipes where it asks for vigorous boiling or gentle boiling. There could be two reasons for that. Number one, the people that wrote the recipe, they may not know very much about physics. They may not have had or may not remember their physics lesson, and they may actually think that boiling vigorously will cook the food faster, and it's not actually true. What boiling vigorously may do is that the increased amount of bubbles that come to the surface of the water actually kind of agitate the food a little bit. And if you're dealing with food like pasta that you don't want to stick together, it helps to stir the pot and also to boil it a little bit more vigorously to keep the food from sticking together. But the pasta doesn't cook any faster because it is not the amount of heat energy that cooks the pasta. It's the kinetic energy of the molecules, which is not increasing while the water is boiling vigorously. So that's the best answer to that question. All right, at this point on your notes, we need to go over a little bit of math, and I want you to draw a box over here on this side and write this. EQ stands for equation. There's an equation you need to know for phase changes. This is a phase change diagram, and remember that at any one time you can either have a change in temperature and a change in phase. If there is a change in phase in the problem you're reading, your equation to use is this: Q equals mH, and H can be either V for vaporization, so here's vaporization, or F for fusion. All right, and if we look at the if I can get a glare off of this, if we look at the equation chart, you'll see number 72, 73 say heat of fusion, heat of vaporization. These are the numbers that are meant by the HV and HF. There's two of them for a reason. Fusion sounds kind of like freezing, and it is. It's bringing molecules together to become a solid, right? And so when you have freezing, you're going to use the heat of fusion. When the problem is about freezing, you're going to use the heat of fusion. But also remember that melting is the same process, just going in a different direction. So if it's either about melting or freezing, heat of fusion will be your guy. But if the problem is about boiling, which is vaporization, or condensation, then you will instead use the heat of vaporization for that problem. So if the problem is about either of those, heat of vaporization is going to be your guy. So just write a few things down. Q, we're going to talk about in a minute, but Q is heat energy, and just like any other form of energy we will discuss in this class, the units for Q are joules. M is mass, and it's in kilograms. We know that already. And then H, again, is called the heat of vaporization or the heat of fusion. And what the heat of vaporization and fusion really is the amount of heat. Notice that the units of these numbers, heat of fusion is in joules per kilogram, vaporization joules per kilogram. What that is the number of joules of energy, the amount of energy that must be added to a substance or taken away from that substance in order to change its state. The amount of energy that must be added specifically to 1 kilogram of that substance. So the heat of fusion, for instance, is the amount of heat we have to add to 1 kilogram of water, in this case, to melt that 1 kilogram of ice. Or it's the amount of heat that must be removed to freeze that 1 kilogram of water. That's what heat of fusion, heat of vaporization is. As an example, flip to the back and let's look at number 2. Number 2 says you're asked to melt. Stop right there. The first 5 words give me a lot of information already. First of all, when you read these problems, you need to be thinking 2 things. Right? 2 things. Either do I have a temperature change or do I have a phase change? PHA. Remember that there's only one of those 2 at any one time. You're either changing temperature or you're changing phase. Since this says melting, I know that I have a phase change, PC. And I also know that that phase change is melting. And remember, in a phase change, this is our equation, and I need to decide whether I'm using the heat of vaporization or the heat of fusion. So if I'm dealing with melting, I've already told myself that heat of fusion is going to be my guy. So I already know that I have a phase change, and in a phase change, this is my equation, Q equals mH. And since I have melting, I'm going to use H sub F, the heat of fusion. Let's go on. 100 grams, that's the mass, and we need to change that to kilograms. So you move the decimal 3 places to the left, which is 0.1 kilograms. You're melting this mass of ice at its melting point. All this is telling you is that there is no change in temperature, and you should already know that. At a phase change, we don't have a temperature change. How much heat is needed? They're asking us to find Q. Alright, so now this becomes pretty simple. All we need to do is plug in our numbers. The mass we said was 0.1 kilograms, and the heat of fusion of ice I will get from the chart. Heat of fusion of water, actually, we know ice is water. And the number is right here, 3.33 times 10 to the 5th. So that's what I'm going to put in here. Joules per kilogram. And if I multiply those together, I'll find that I get 33,300 joules of heat. Their answer was in kilojoules, and if we change ours in kilojoules, all we need to do is move the decimal 3 to the left, which gives us 33.3 kilojoules. And it's okay that they got 33.4. The reason they did is because they used a slightly different heat of fusion, and that's okay. Alright, so that's phase changes.